Hello dear students. Today in this class we will discuss the kinetic energy and the potential energy of a particle in an SHM. Before going to this topic, we were discussing that is of phasor diagram. Using phasor diagram we can going to find out the equation of a particle in simple harmonic motion. So along with this we have solved some problems also, and in the previous class I had given one question to solve for your sake by giving that the particle executing the simple harmonic motion initially at x is equal to minus a raised to a divided by root 2, and it is initially it moving in the positive x direction. So we need to find out the equation of a particle, means in a simple harmonic motion, where it is already given the position of particle is x is equal to minus a by root 2 here. That means it's already getting the conclusion that particle is not at the mean position where x is equal to 0. So we have x is equal to minus extreme position and x is equal to plus positive direction. So already x is there here where it is in a negative minus a by root 2. So this will give you x is equal to minus a here. This is x is equal to 0. This we know at t is equal to 0 here. But when particle is moving from mean position, now particle is at a negative extreme position before minus e, means here it is x is equal to minus a by root 2 it is, right? So from here initially it is moving positive direction. So here it is initially moving positive direction, means it is moving positive direction. Here it is moving positive direction, means to do this function is already moving. With the help of phasor diagram, we'll draw a phasor diagram here. We can able to solve the question, is it possible? It is possible, right? Now think it is x is equal to positive, x is equal to minus a here. So particle is there here. X is equal to minus a by root 2. This is x is equal to 0, right? It is moving initially. Two part will be given. See here also it may move in this direction or it may move in this direction, but particle is at the negative extreme position. It is so negative extreme position. So we have this particle is moving in a positive direction. It is so positive direction means it is moving in this direction. So draw here. So this point will be what here? T is equal to 0. So this point at t is equal to 0, where it begins to execute the simple harmonic motion. At that time we are taking t is equal to 0. If particle is moving from initially this, so this point will be 0. Now particle is said to be, it is already in a negative extreme position. It is, that is x is equal to minus a by root 2. If you go ahead with this, so it is moving in a positive direction. So what we are getting? We are getting this part. So this is theta. Theta means what here? This is a omega t. So making use of your general equation, x is equal to a sine omega t plus phi it is. So a sine omega plus omega t plus phi. So look at here, this is a negative extreme position. It's moving in a positive direction. It is. So which equation we have to find here? General equation we are taking, whether it may be a positive. We will discuss that also. When particle is moving from negative extreme position, we have a general equation that is of x is equal to a cos omega t, negative, no, so that's why it is minus. So this form we are getting later doing this one. So that will be proved or not, let us cross check. So we are taking a simple harmonic motion general equation. So what is this? This is of a here, a by root 2 it is minus, this is of a. So what we are getting here? Opposite upon hypotenuse. Cos, no, this is the projection. So this is the projection on diameter here. Adjacent base by hypotenuse. So directly you can take a theta value we not know. We want it. So that is of adjacent a by root 2 by a it is. So a get cancels, remains with 1 by root 2. So cos theta here. Theta is a cos inverse of 1 by root. Cos inverse of 1 by root 2 is what here? That means minus, right? So minus will be remains here. Cos inverse of 1 by root 2 is 45 degree it is. So 45 degree. So this part we got it, theta is 45 degree, means this complete part is 90. So 90 minus 45 degree is what here? 45 degree only. But I said always a distance or a displacement is measured from mean position it is. Wherever may be the particle, x should be measured from the mean position. Similarly, phase. This part will be initial phase. So you have to start from here to next it is. So it is moving from here to here it is. This part, right? So this is 90. This is 90. So this is how much it is? 90. So total phase will be, that means this part it is. So this is the phase, no, this is the complete phase here. But initially it is what? 270 plus 45, means theta is 45 here. So this will becomes 5 it is. 90 plus 90 plus 90. 180 plus 90. 278. 270 plus theta. So substitute here. X is equal to a sine omega t plus phi it is. So what you are getting? A sine, that is of 270 plus 45. So 270 plus 45 here. So look at this part. This is what? 270 plus theta. That means it is in the form of 270 plus theta it is. So this part I will take it as just a theta it is. To matches with the allied angles that we have, right? So that is of what? 270 plus theta. 270 it going to be changes with the cos, right? No. So this is what we can go ahead with the allied form here. 0, 180, 90, 270. So 90 and 270, sine will changes to cos and cos will changes to sine. So here in the form of 270 also, sine changes to cos, cos changes to sine. So sine changes to cos here, right? Next, cos theta. Theta means what here? Omega t plus 45 degree. Next, in second quadrant, sine will be positive, but 45 degree is negative. So that's why 45 degree is a minus negative here. So this is the direct conclusion we are getting. Direct conclusion we are getting that, so particle is moving at the negative, particle is at the negative extreme position, but it is moving in a positive direction, means in this part. Look at this, our general equation. If particle is moving from a negative extreme position towards the mean position, we are getting minus a cos omega t. If particle is there in the positive extreme position, we have an equation. What is that? It is moving towards the mean position. We have x is equal to a cos omega t plus this. moving towards the mean position or away from the extreme position. This part will be positive, but particle is moving from extreme position. If particle is moving from mean position, we have a general equation that is of A sin omega t. Moving from mean position to negative extreme, minus A sin omega t it is. This we know. It is already given, particle's position is minus A by root 2. This concept you have understood, directly you can apply the phasor diagram. You can able to find out the form here. So this is about the phasor diagram. If you go ahead with the simple form, that is, we don't want phasor diagram, we want only from the simple harmonic motion only, that solution means just put it here. This is the general equation, right? Apply here. What is that? You can go ahead with the same form, simple harmonic motion equation only. You can try, you will get the same answer. That is what? X is equal to A sin omega t plus phi it is. So x is what here? Minus A by root 2. That is A of sin omega t plus phi. So A get cancels, remains with the root 2 minus, that is of sin omega t plus phi here. So we want to find out the phi here. It is, so omega t is what here? Theta. So sin theta, that means theta, t will be what here? 0, because it is moving from here. So it is remains with what here? Phi. So 1 by root 2 minus. So sin inverse of 1 by root 2 phi. So 1 by root 2 of phi. We are getting 45 degree. So phi is equal to 45 degree. So minus will be remains as it is, because of it is in the position of negative extreme direction. So we got it phi here 45. Here also got it phi is 45 here. But the thing is, journey starts from 270 to 270 plus 45, means theta is 45 here. Right, theta is 45. Next you have to go ahead with the velocity form, because velocity will tells the motion of a particle, but displacement does not tells the motion. I mean to say that velocity execute in which position particle is moving or executing simple harmonic motion. So directly you can go ahead with the velocity here. What is this? A omega sin cos omega t plus phi here it is. So A is A here, omega cos omega t. If t is 0 means it will be remains as a phi here. So when particle is moving, velocity should be greater than 0, where velocity will be 0 at the extreme position, but it is moving, so cos phi must be greater than 0. So we are getting 45 degree here, right, in the displacement form. Cos phi should be greater than, means this phi should be matches with the velocity also. So cos will be positive at first quadrant, right, but negative in the sense means it will comes as a negative here. So second quadrant cos is negative, means particle is at the negative extreme position. So cos phi equal to 45 degree also. So you can just substitute here, you will get it minus v is equal to minus a omega cos omega t plus 45 degree. So this is also same answer you are getting here. Whichever method you can use, as a simple harmonic general equation also, or the phasor diagram also, you will get the same answer. But the thing is, you should be perfect in which part I am utilizing to solve the equation of a particle in simple harmonic motion. So better in the sense, you can practice until you get the perfection in this method. Either you can use the phasor method, either you can use the simple harmonic motion equation also. Let us ahead solve some of the problems also. You can collect the mini kind of problems, different varieties of problems. They may give you the position of x is equal to minus root 3 by 2. It is moving in a positive direction. So this kind of questions will be arises. If you want, you can try this example in yourself and you will get a equation of both the method. You can try phasor diagram also, you can try, and simple harmonic motion general equation also you can try. You will get the same answer it is. So we should find the phase, that is phi initial phasor it is. Next we will get the complete equations. So by discussing the phasor diagram here, very important part, that is we will move towards the kinetic energy and the potential energy of the simple harmonic motion it is. Later we'll discuss the graphs in it. One by one we will going to study very detailed form of it. Yes, if particle performing a simple harmonic motion, it acted by the restoring force, which is always directed towards the mean position. So that we know here. So when particle is executing the simple harmonic motion, say this is of mean position where theta is equal to 0 and t is equal to 0. When we have to take t is equal to 0 here, when particle starts executing the motion from the mean position, or else when which position of a particle executing simple harmonic motion, that time we have to take it as a t is equal to 0. Now if particle is performing simple harmonic motion, it is acted upon moving towards the mean position, wherever it is going positive extreme position or a negative extreme position it is, right? Let's try to move towards the mean position only. This is the first task it is there in the simple harmonic motion. So once it is just moving and coming back to original position, and it will not stay here also. Particle is not staying here, it's not staying here, it's not staying here. So it is try to come towards the mean position only. So repeatedly coming back to its original position. That is simple harmonic motion at a particular time instant it is. When particle is in motion, means particle has an energy. Whenever the particle is in motion means it has an energy. So motion means particle is in motion means it has an energy, that is of kinetic energy. It's executing a motion means it tells that kinetic energy is there. When kinetic energy is there, obviously potential energy will also be experienced by the particle. Experienced by the particle, right? So when potential energy and the kinetic energy are experienced by the particle, then total energy of the particle is sum of the kinetic energy and the potential energy here. So here in simple harmonic motion, kinetic energy experienced by the particle and potential energy both are conserved here. Conserved in the sense it's going to be vary. See, look at here, where velocity will be maximum at the mean position, velocity will be minimum at the extreme position. Whatever may be the extreme position, whether it is a positive extreme or it is in a negative extreme. Similarly, as it is a moving particle from mean position to extreme position, velocity decreases and becomes equal to 0. Means kinetic energy is coming to the action. It's moving, velocity decreases and it becomes 0 here. That means storage is there here also, storage is there here also. So potential energy is also there. It's going to be very continuously with respect to the mean position or the extreme position, because velocity is going to decrease here. Maximum decreasing and it becomes 0. That means kinetic energy and potential energy both are variable here in simple harmonic motion. Both are variable in simple harmonic motion. When these two are variable, then sum of these two, potential energy and kinetic energy. Potential energy and kinetic energy will be the total energy, and that is remains constant. So that is remains constant. That means energy in the simple harmonic motion is conserved, whether it is a variable or a constant. When potential energy, kinetic energy of a particle executing the simple harmonic motion experiences the variable form, means it's every time it's going to be vary. When these two energies are variable, then some of these two energies will be constant. So that only we are going to discuss here. That is force which is acting on the particle directed towards the mean position. That we know. So what kind of force it is? F is equal to minus k x here, right? So this force which is acting, it is opposite to the direction of displacement. Particle is moving here, but force is applying towards mean position, means opposite to the displacement. What we have discussed in the previous chapter, force which is acting on the body, it's along the direction of displacement. But in the simple harmonic motion, force which is acting on the particle, which is opposite to the direction of the displacements. This concept you have to understand, and you have to compare and remember this. So when force is opposite to the direction of displacement, means particle is executing the simple harmonic motion. So some of the energies experienced by the particle is conserved here. That means constant. Now force, we know here F is equal to minus kx, it's already there. When which is acts on the particle, that negative sign indicates it is opposite to the direction of displacement. When force is conserved, when energy is conserved, then it's totally depending upon the final and the initial point here. The conservation means what? Totally it is depending upon the initial and the final test. So potential energy, kinetic energy is depending upon initial and final point. That means it's going to be a variable, but the sum of these two forces will be remains constant. To understand this, so we'll do, to displace the particle. Displace the particle means executing the motion of the particle. We need to do some work here. That means let us go ahead with understanding this by explaining part. We'll try to make the body to be under the work. Work in the sense what? It has to exhibit the motion here. Now I'll do, this is the positive extreme position, this is the negative extreme position. Until you get confirmation and perfectness in this, you can make use of the diagram only, right? So particle, it is the moving in this direction. We are taking positive direction only because it is very comfortable to understand, right? So when particle is executing in this direction, will in this direction means energy is experiences, because it begins in the motion. So once it is executing in this direction, we'll do small work. Small work means small work done to displace the small distance. So what kind of work it is? Small work, right? So if small work is done in displacing the particle in small displacement, that means we have a work done. What is that? F into S. Force is there here. What kind of force it is? Simple harmonic motion. F is equal to minus kx it is. So minus S means what here? D. S is equal to dx, means small displacement it is. Small displacement. So dx. Small work done, dw it is. Small work done in doing the small displacement. Already it is there in a simple harmonic motion. Experiences the motion here. But we are taking small work done. Small work done, small displacement. So that's why it is taken here. But dw is equal to, what is this force? Force is minus of kx. So dx. So you will get x dx here, dw. This whole concept should be applied to the complete displacement, complete work done in showing the particle is executing the simple harmonic motion, or else it is experiences the moving in the extreme position. So integrate it. So when particle is moving from x to is equal to 0 to x, small displacement we have taken, no? So 0 to x, 0 to x, or you can take a 0 to a when it is making the exactly extreme position. So dw, integration of dw will be w here. So k is a force constant which is acting on the particle, right? Integration of x of dx 0 to x it is. So you will get x square of 2 0 to x it is. So we are getting x square 1 by 2, I will take it outside, minus of 0. So that means 1 by 2. So that is of 1 by 2 minus the potential energy. Also, sorry, work done is equal to 1 by 2 kx square here. So kx square, look at here, this work done is equal to the potential energy, half k x square. By seeing this equation, you can't judge this is the kinetic energy. No, this is potential energy it is. So this is of potential energy. As we know here, acceleration of a particle executing the simple harmonic motion, we can take here f is equal to minus kx here. So f is equal to m into a is equal to, we got it here, f by m, f in this case minus k by m, x here. So a is equal to minus omega square x. We have written, no, we know this. So omega square is equal to what here? K by m. As k is equal to omega square m here, substitute in this form. So what we get? Work done is equal to 1 by 2 kx square it is. So in place of k, just substitute the omega square m here. So 1 by 2 omega square m of x square here. So this is work done, and this work done is equal to the potential energy. So u is equal to half omega square m x square here. This is of potential energy experienced by the particle when it is executing the simple harmonic motion it is. Then we'll move towards the kinetic energy. We have a displacement of a particle. We have done the displacement. This is about the work done in moving the small displacement, and it is applied to the complete displacement. I mean, experiences means before going to be in the motion, what is happening here? What kind of energy will be there? So work done. Work done is equal to the potential energy. Potential energy means what? It is in the form of storage energy, but particle executing the simple harmonic motion means it is just extended, means it's going to be kinetic energy is going to be decreases, and it is in the form of storage. That means it is potential energy. Now we have displacement general equation as x is equal to a sine omega t. Y means it is moving from here, from the mean position. We have a velocity that is of omega square of root of a square minus x square here. We have a kinetic energy. What is that? Kinetic energy is 1 by 2 m v square it is. Just substitute the v value in this kinetic energy here. So what we are getting? I think I'll just erase this one. So we'll get the kinetic energy that is of half m v. In place of v, I'm going to write it here, omega square, right? Sorry, here velocity will be omega here, omega a square minus x square here. So this part is nothing but the k value it is. I mean, k we have got, no, omega square m here. So 1 by 2 k a square minus x square. So this is of kinetic energy of a particle experiences the simple harmonic motion here. So when will be kinetic energy maximum? When will be kinetic energy minimum? So when will be the potential energy maximum? When will be the it is minimum? So let us go ahead with the potential energy general form, that is of 1 by 2 k x square it is. This you should remember, and k value it is already given, just to substitute in both the form of the energies. And these two, sum of these variable kinetic energy and potential energy of a particle is going to be constant. So I said in both are variable, it is. Both are variable, but the sum of these two energies. So sum of potential energy plus kinetic energy. In displacement form I am showing you. First, displacement means what? It is x form it is. What is that? 1 by 2 kx square it is, plus 1 by 2 k a square minus x square it is. A square minus x square here. So sum of the energies of the particle, how it is going to be said to be as a constant, that I am showing you here. That is of T is equal to 1 by 2 kx square plus 1 by 2 k a square minus 1 by 2 k x square it is. So 1 by 2 kx square, 1 by 2 kx square get cancels, remains with what it is, 1 by 2 kx square it is. So this will be remains constant it is. So this will be remains constant. What is this A? A is nothing but the amplitude, K is nothing but the force which is acting. Constant force in the simple harmonic motion. So this part will be remains same. So we have understood with this displacement of, well, displacement is taking place by the particle. At that time energy is a constant. Now we'll check the constant total energy experienced by the particle in a time also. So that also we will discuss. Now we'll check the total energy experienced by the particle. I will write it here. What is the total energy? Half ka square here. Half ka square. Now I'll erase this one. We'll cross check with the variable, time it is. So in time part it is, we have a general equation that is of a sine omega t here. V is equal to what? Dx by dt. That means a cos omega t into omega here. Derivation of x. So a omega cos omega t here. Next, kinetic energy. We have kinetic energy. The simple form kinetic energy is half mv square here. V value we got it here. Just substitute 1 by 2 m. V square is what here? A square omega square cos square omega t. Yes. Now look at this part. I'll rearrange this one. 1 by 2 m omega square a square of cos square omega t, because this part will get it as a k here, omega square m. So 1 by 2 k of a square cos square omega t. Right? So this is about the kinetic energy here. Now we'll move on towards the potential energy. Potential energy means what here? Half potential energy is how much it is? Half omega square m x square. So x square is this one. So I'll write it first. So 1 by 2 omega square m of x is what? A square sine square omega t. So sum of these two. By here only you can guess it. I'll just erase this part. So sum of energy, potential energy plus kinetic energy here. Potential energy we got it here 1 by 2 m omega square a square sine square omega t. Kinetic energy we got it here Directly I will write it here, 1 by 2 omega square m of a square cos square omega t. So this I will write it as a k here. That means 1 by 2 k is a common, right? Then a square is also common here. Sine square omega t plus cos square omega t. So this is 1 remains with 1 by 2 k e square. So potential energy, sum of the potential energy and the kinetic energy at the time also. Why we have taken time is this part t is there here, and potential energy means particle is with the time period here, and potential velocity is also. What is this velocity? It tells the motion a omega cos omega t. So both are there, which is having the time period. So that also kinetic, total energy will be remains constant. Look at here, 1 by 2 k a square for displacement, where we have taken displacement as in the form of half k a square minus x square it is, but here half mv square with the help of velocity also we have taken. But in both the time period as well as the displacement, total energy of the particle executing simple harmonic motions remains conserved, or else it is constant. We can say that it is a constant. It is total energy will be remains constant here. Now come to the part of when the kinetic energy and the potential energy will be maximum when it is executing the simple harmonic motion. Now we have velocity of the particle will be maximum at the mean position, and it's going to be 0 at the extreme position. Now with the help of this, again particle executing simple harmonic motion here, positive extreme position and negative extreme position here, right, where t is equal to 0, we'll take it as particle is moving from the mean position only. Now we have a kinetic energy that is of 1 by 2 k of a square minus x square. This should be remember, right? Now put x is equal to 0 here. 0 in the sense mean position. What will getting? Kinetic energy will be 0 in the sense remains with only this part. So 1 by 2 k a square, correct? So this is maximum. Maximum in the sense what here? Kinetic energy will be maximum at the mean position. That means half k a square it is. So at this point kinetic energy will be maximum it is. Now that indicates here velocity is 0 at the extreme position, means kinetic energy will also be 0. 0 in the sense what? It is going to be minimum here. Let us go ahead. X, just put it x is equal to a, means extreme position. So x is equal to plus a it is. Now what will be the form? Kinetic energy is equal to 1 by 2 k of a square. In place of x, I'll just put a here, x square remains with what here? 0. So kinetic energy will be 0 at the extreme position. When you put x is equal to minus a, means a negative extreme position. What will be the negative extreme position? Put x is equal to minus e. So kinetic energy will be 1 by 2 k of a square minus of minus a square it is. So totally again it is also becomes 0. That means extreme position of a particle executing simple harmonic motion, kinetic energy will be 0. Kinetic energy will be 0, or sometimes we'll take it as a minimum also, where velocity is going to be 0 here. Now similarly if you go ahead with the potential energy. So when potential energy will be maximum, when potential energy will be minimum here. So potential energy we have, what is that? 1 by 2 kx square it is in part of I'm telling here in part of it as displacement, right? So put x is what we are getting here, 1 by 2, this whole part, k 0, means potential energy will be equal to 0 at the minimum position. Look at here, I'll just write it. Potential energy is equal to 0 at the mean position. Then what about the extreme position? What will be the extreme position? Put x is equal to a, potential energy will be equal to 1 by 2 k a square. It is x is equal to, that means potential energy will be maximum. We are getting 1 by 2 k a square here at the extreme position. Which will be maximum at the extreme position? Acceleration will be maximum, where we are getting minus omega square x here, right? And force is also maximum. So we have not taken force is acting on it. So force, acceleration, potential energy will be maximum at the extreme position. Kinetic energy, acceleration is equal to 0. Force is equal to 0 here. And in the mean position, kinetic energy is maximum here. Velocity is also maximum here. So these points you have to remember. When the kinetic energy will be maximum, when the potential energy will be maximum. So kinetic energy will be maximum at the mean position of a particle executing simple harmonic motion. Potential energy will be maximum at the extreme position, but the mean position it is 0. So according to this concept, if you plot the graph, so what kind of a graph you are getting? Let's go ahead here. So I have written in the diagram only which is maximum, which is minimum at a particular respect position here. We'll go ahead, plot the graph of it. We'll get to know that. So where and minimum. So let us go, x is equal to minus a it is, x is equal to plus a it is. Now kinetic energy will be maximum here, so I will write it here maximum with respect to the displacement it is. At the point x is equal to 0, I will write it here. Kinetic energy will be maximum as we go ahead with the half k x square it is, I mean a square it is. As it is moving towards the negative, it becomes 0. So 0 it is. As it is moving towards the positive, it becomes 0. So how we are getting here graph in this manner. So this is of kinetic energy. Mean position it is, kinetic energy is maximum. Then let us go ahead with the potential energy. So potential energy will be 0 at the mean position. That means 0 only, minimum it is. What will be the potential energy at the extreme position? That is of 1 by 2 k square. Here also 1 by 2 k square it is. Maximum it is with respect to point, mean position it is a 0. Again it is maximum at the extreme position. So you are getting in the form of this curve. So this is of in this format. So this part is potential energy here. So by drawing this, don't bahad the diagram also. Nowadays it is also started. The meaning, if you have understood, there is no need to bahad the, or no, there is no need to practice the diagram here. Potential energy will be 0. Make it as a downward here, because x is equal to 0 here. Minimum. When it will be maximum? At the extreme position. So it is going up here. So in the both are appearing as a parabolic only. But the thing is, when kinetic will be energy will be maximum, at that point potential energy will be 0. When kinetic energy will be 0, at that time potential energy is maximum. And this concept you have understood, means it is very easy to solve the problems relevant to the kinetic energy. Finding the kinetic energy, finding the potential energy of a particle executing the simple harmonic motion it is. So this is about the potential energy and the kinetic energy of a particle. Now let us take a 1 or 2 problems to understand the better form of how to find the kinetic energy potential energy of a particle here. So let it be here. With the help of this diagram only, we will take it here. Kinetic energy will be 0, potential energy will be maximum here at the extreme position it is. Now find the total mechanical energy. So find the total mechanical energy of a particle undergoing simple harmonic motion of a mass 2 kg and x is equal to 2 sine pi by 4t plus pi by 4 it is, assuming that velocity is equal to 0 at mean position. So we need to find out the total mechanical energy. Here what do you mean by total mechanical energy? Sum of the potential energy and the kinetic energy of the particle. So that is nothing but the mechanical energy. So don't get confused. Total energy of a particle, or else we can say that the sum of potential energy and the kinetic energy, will call it as this is the total mechanical energy of a particle it is. So total mechanical energy of a particle. Now we need to find out its mechanical energy when it is undergoing the simple harmonic motion of a mass 2 kg. So particle is there of a mass 2 kg undergoing simple harmonic motion. So if it is not giving, assuming that a velocity is 0 at the mean position, obviously velocity will be 0 at the mean position, but it is nothing but the, I think it is wrong here. Velocity will not be 0 at the mean position. It will be maximum it is. So we'll take it as a, assuming that v is equal to 0 at the extreme position. So extreme position it is. Right. Now let us find out here potential energy and kinetic energy simultaneously. So potential energy we are having half kx square here, right? That means 1 by 2 k we know here, that is of omega square m here. Okay, now omega square m x square here. Kinetic energy, that is of half k a square minus x square, it is a square minus x square. This one we have. Even the k value you can substitute omega square m here. If it is not needed here, but already x is given. So just compare with this. Okay, now total energy will be 1 by 2 omega square m a square it is. Omega, in place of omega here, I am going to write it here, pi by 4 whole square. M is 2 kg, that is of into 2. A square is given here 2, that is of 2 whole square it is. Right, now we'll go ahead with the final expression. T is equal to 1 by 2 omega square m a square it is. We got a total energy 1 by 2. Omega is what here, pi by 4 whole square it is. M is 2, a is 2, so 2 whole square here. So what we are getting, 1 by 2 pi square 16 into 2 into 4. So 2 ones are 2 ones are 4 ones are 4, 4 fours are. So pi square by 4. So this is the total energy of a particle experiences the simple harmonic motion when it is undergoing the simple harmonic motion. So by this, we have got the conclusion that kinetic energy and the potential energy, the particle executing simple harmonic motion, is a conserved,